Greetings, Jan. You're on mute.
Oh.
Hey, I was muted.
Do you, just quickly, do you agree with the sentiment that Starks and Snarks could be used as a scaling mechanism? In that if technically all the data is not being used in these computations, you can just assume then it's automatically scaling, potential scaling solution?
So the big problem that Starks still have, and we haven't discussed, and we'll kind of only briefly touch on today, is that Starks work really well for certain classes of programs, but don't yet generalize to arbitrary computations. So as a scaling solution for some specific things would be very, very helpful. For others, I don't see it yet.
Cool. Do you like Snarks and Starks overall, or is it still an unclear technology?
It looks good. I mean, the stuff that you can use it for seems like it's well thought out and people have solved the problems. And like just last week, I saw a paper on the archive. So like improving some aspect of it. It's clearly undergoing extensive research, so it'll get better. And I think it's really cool for what it does do, but it's, like I said, I don't think you can do arbitrary computations just yet.
Cool.
We'll just wait a few more minutes for some stragglers. We'll aim to start in 2 or 3 minutes. Okay, I think it's about time to get started. It's 3 minutes past. Might as well start. Can't wait forever. And there will be lots of material. Martin, could you mute your mic? Thank you. Okay, so part 3, Starks. Remember, what we're trying to do with a Stark is a method for provable privacy and integrity of arbitrary computations. And I remember the first time I said stuff like fully arbitrary computations, and Leo asked, "Oh, what about non-determinism?" I think the answer to that is almost certainly no at this point. But it's, you know, I don't have a counterexample. It could work, probably won't. Let's assume it's not. The reason it won't work will become clear in a slide or two. And we do want these things to be as efficient as possible. We don't want to do too much extra work in addition to the regular work we'd have to do in order to execute these code or these programs or verify that these programs are run. So we want both sides of the protocol to be very efficient. So provers shouldn't have to do more than just running the computation. They will have to do some because just how it goes, but hopefully not too much more. And verifiers would ideally like to do less than running the entire code themselves because they don't want to run the entire code themselves. And we don't want to trust it transparent. So this is the familiar expectation of what we're trying to build. And we're going to just conclude this with the third blog post by Vitalik on Starks, which has been sort of adapted here for more clarity. This is a slide that you've seen a few times now, and it's from the Israeli professor who develops Starks, actually developed the techniques in the last part. And it's a nice summary of what we're sort of expecting. We're expecting that we have some program that we're going to encode as some polynomial, or rather points on a polynomial, and then we're going to check our boundary conditions, and we're going to check that some invariant holds throughout this execution. And this is the general strategy we're going to take to solve the Stark problem, and we've sort of discussed some issues with this already, right? Part 1 and part 2 have said some things, and there'll be a recap on the slide, the next slide. The problem is that this encoding of the polynomials is almost certainly where the non-determinism would become impossible to encode without a lot of effort. Again, no explicit counterexample known to me, but it's probably really tough to encode a non-deterministic program as such a polynomial where you can say that from step I to step I plus 1, some invariance still holds down to 0. So for now, we'll assume that things are deterministic and say on one processor thread scheduler, so it's even easier. It's still non-trivial. Even in that case, what does it mean to encode points what does it mean to encode an execution trace as points on a polynomial is very much outside of the scope of these blog posts. And the example we use actually implements a nice actual real Python code that someone might actually want to use, but it's a very simple one still in many respects. So it doesn't handle multiple variables, and we actually only care about the a single variable output relative to a single variable input. So if you're dealing with more variables, would you encode things like by concatenating a specific order or doing something else? The answer is presumably yes, but it's presumably where a lot of the work is going for arbitrary computations as well. So we'll just skip that for now, and I will show you something that's real, but it's not as real as maybe I promised in the past, because I thought this blog post also said more the last time I read it, and I was wrong. So what have we done so far? First part of this series on Starks in the blog post was probabilistic proofs of polynomials. How do we amplify errors so we find that everything, anytime someone cheats, we actually catch it. And we did this by sort of saying, here's a polynomial, and we'll multiply by something else. We'll have a bigger polynomial. And so if you screw up somewhere, you're probably going to screw up in like 10 million other places as well. And so if someone catches you, or someone guesses anywhere, you're probably going to catch an error with very high probability. And even if you don't, you just do some small number of checks to really check it. But there was a slight issue with that argument, whether or not you guys caught it or not, or whether or not I conveyed it accurately. Turns out for a lot of these values, the prover can be malicious and just generate random values and shove those into our Merkle tree and commit those. And then everything looks like it works, but in fact it doesn't. In particular, the problem is that we have no guarantee that all these things are from the same low degree polynomial. And so we had to spend a lot of time overcoming this issue and introducing techniques for low degree polynomial testing, which is what we did last time. It was a little bit less clear than the first part, I'm sure. Luckily, we're going to use it as a black box in this case, and so if it's still unclear, talk to me offline or look at the source blog posts, or find your own reading. Obviously, I'm trying to help as much as I can, but as someone who's not developed this theory, I'm definitely not necessarily going to be able to answer every question right the first time. The one question I did have from last time was why was that certain value 1,000 chosen? It looks like it's mostly for an optimization tactic, and also why the p of x's that we used in that had to have some degree, and that's because in that case we strictly chose more than that degree, so it has to be on the same one. When we use this as a black box, I'll explain that again. Any questions about what we've done so far or what we're trying to do? Okay, not hearing any. So today we're going to try to talk about how do we actually prove that someone executed some specific piece of code properly. Our example will be implemented in Python. So we're going to write some code that's in Python. Well, I'm not going to write any code. You're not going to write any code. We're going to read a lot of code, and we're going to ignore a lot more code that shows how you would actually check, like build a Stark for some code and actually verify that Stark. And so most of the pieces of Python we're going to see is actually the infrastructure, so the way to build or check proofs, as opposed to the actual thing we care about executing. Because the thing we care about executing, as we'll see in a slide or two, is very, very simple. And we're going to do what we think is the optimal, but I don't think there's a proof of optimality in terms of complexity, where the prover will only have an overhead of an additional log t factor, which is pretty good, and the verifier will verify in log squared t time for some computation that takes t steps, which is strictly less than t if t is sufficiently large. So this is pretty good. In neither case will I present a complexity analysis because the blogs don't, and I didn't think it was that particularly interesting. Understanding how they work and then optimizing is definitely the best approach to take here, because the concepts are hard and then optimizing them will also be hard. Right? So the specific thing we want to show actual computations of is mimic. If you've talked to Vitalik recently, he really likes this function, in large part because I think of the Stark potentials and its ability to be used as a VDF, which is a verifiable delay function, which is something that also comes up all the time in blockchains, because they might be a useful source of randomness. And so VDFs are these really cool things, and this one's particularly nice because it uses very simple operations. And the simpler the operations, the easier it is to create a Stark. The easier it is to create a Stark, the less the size of the proof of the Stark is, and the more useful this protocol actually is, because you put it on a blockchain. So Mimic was produced by these people, and it's very simple. You give me an input, it's an integer over some finite field, and then I cube it, divide by the modulus of my finite field, right? We've seen modulus last time. Finite fields, think about clock arithmetic, right? So you give me 3, I cube 3 divided by, say, our clock, which is 12. 3 divided by 12 is the remainder of 0. My new value is 0, and then I add some round constant, k1. This is my first time going through this loop. So I pick k1 out, and I add it to this. So k1 is 2, and now my new value is 2, and I cube that, and the process repeats with the new k value. That's the whole thing. We do this for some number of rounds, and the output is whatever x is at the final stage. Very simple arithmetic program. Can be used as a hash function, can be used as a verifiable delay function. Why? Well, because to verify it, you can think of taking this process in the forward process. You just cube things, add things, and cube things repeatedly over and over again. But actually, for some cost overhead in terms of time, you can go backwards. So what you can think of is, say, give me a proof that you actually did it backwards. So if I give you some output, what was the input to this? And sort of that's what you want to generate the proof for. And this is slow because the modular arithmetic for inverting the cube is slightly slower than actually cubing it. And so what ends up happening is you can verify it about 100 times quicker than you can to actually prove it. And so the bottom is standard mimic, the top is sort of backwards mimic, and that's the thing they want to sort of prove. Again, you use the same constants k. We're also going to assume k has some small number of different distinct values that are ordered. So maybe 64 of them, because that's what the example does. So basically, if you query the constant for around 65, you're going to be taking that modulo 64. So you'll take the first constant again. The constants will be the same whether you're proving or verifying in this example. And there seem to be known to both participants because the verifier presumably says, here, do this work, and then they get the work to be done. The first polynomial we'll talk about today is the polynomial of these constants, these k values. So I'll define k of x to be the k value when x is the appropriate I. So k of 1 is the first constant, k of 2 is the second constant, so on and so forth. And note that I don't really care what k of x does after 64 because I'm doing this all modulo 64. Do you have any questions about Mimic? Careful readers will note that there's something weird, right? The weirdness is the inversion of x to the cubed. X to the cubed is inverted in our prime by taking x to the power 2p minus 1 divided by 3. This is sort of less obvious than the standard cubed root.
Why is that?
Good question. Because we're going to choose a nice prime that is of the form 6k plus 5 for some value k, which is not the same polynomial k, and then the proof is on the bottom of the slide. So by Fermat's local theorem, you take x cubed and raise it to this power of 2p minus 1, and at the end of the day, you get x back because of the fact that our modulus will be prime and it has this nice form 6k plus 5. So it is there. It's not clear, or I mean, it's not like immediately clear, but it does work. It's also not super relevant. Just note that you need an inversion function for your Mimic to go backwards, right? Because if you don't have that, you obviously can't invert Mimic. And so it's kind of awkward, but it's there. And so in particular, we will use this prime number, 2 to the 256 minus 351 times 2 to the 232 plus 1, because it's a nice prime number that is of the form 6k plus 1. And then we're also choosing this because it has some nice properties in that it contains a multiplicative group of order 2 to the 32. For reasons that aren't at all clear yet, because we haven't talked about the reasons that we need that. And they'll come up, and this is unfortunately just the way that was chosen. Assume that we have a nice prime that works for a lot of good reasons. So our modulus will be a prime number. We do get to use Fermat's little theorem a lot. We do get a lot of nice properties by words of unity of that mean value. But the inversion of x cubed is the thing that we need for now. Okay, when you're dealing with prime fields, you need basic operations. You need to write these in Python. I'm going to assume people know how to do modulus, addition, subtraction. But if you don't, here's the code. I'm not going to go over most of the code in any great detail. I'm certainly not going to go over this in any detail whatsoever because modular arithmetic is clock arithmetic, and we've talked about this. If you have any questions and you want me to slow down, please ask me. But there's a lot of material as well, so I don't want to go through every little code. You also need to do modular inverse. Yes, we talked about it. Unfortunately, modular inverse is kind of slow, as I hinted with the inversion of Mimic. Modular inverse is typically slower than taking a modular exponentiation. So this is problematic. This code isn't particularly fast. The 16 Euclidean algorithm is not the worst, but it's definitely not super fast. So we'll do a little bit better sometimes. I'm not going to go over this in great detail, but there's this cool way if you need to batch a bunch of inversions at once, you can do it with a constant number of inversions, namely only one, which is really cool. It's the red one. I won't explain what this picture really means, but it just means after, if you give me a bunch of numbers, I can invert the whole set with only one inversion, which is super cool. We won't go over that, but note you can write it in Python, and here it is. Cool. We now have all the operations we need of a finite field in modular arithmetic in order to make this work. Of course, we are going to be dealing with polynomials. We've already alluded to one, this k of x function. The interpretation of how they're stored will be typically something like this. So we'll have a list of coefficients for the exponents in decreasing order. So the polynomial x cubed plus 2x plus 1 becomes a list 1, 2, 0, 1 because the coefficient of x cubed is 1. The coefficient of, what's wrong? There should be an x squared. So that one was wrong. But the storage should come out all the same. It's just a typo. It should be 1, 0, 2, 1. It's fine. Or you just take it backwards, I guess. You reverse the list. That's also fine. Okay, yeah, so we have a list. This is the code for evaluating a polynomial. It's, again, exactly what you'd expect from your first year calculus. You give me a polynomial and you give me a point x. You put x into all these things and then you evaluate it. Note, of course, again, and don't forget, we're always operating over this finite field. We'll have modular arithmetic used everywhere. So this self-modulus thing will come up a lot. Right? This also keeps the numbers small, which is kind of nice. Everything comes. Okay. Some other things we're going to need. We need to be the ability to create a polynomial with some nice roots. I want a polynomial to be 0 at a set of values. Remember, we had this way of creating such a polynomial. Sorry, I'm burping. We had such a way for creating a polynomial by basically saying for every point that I want to be 0, I'll take x minus that point to be a factor of the polynomial. And this is a function that just defines such a polynomial. So this is also fairly straightforward and nothing super new or super hard. And I'm trying to link this back to the other part, so I'll try to do call-outs to say, oh, this is what we did last time, or this is what we did 2 times ago. And this is something that comes up. It's a common operation. We need some more things. We need to be able to interpolate polynomials. So I need to be able to give you a set of points, and I need you to say, what's the polynomial that goes through all of those sets of points? This was sort of implicit last time. This is what that giant Merkle tree was trying to get the values for, to make sure you could run a function like this to interpolate and then get the values back. But this time, because we want to build a concrete example, this, something needs to be written. This one works. This is Lagrange interpolation. I'm not going to go over how it works. I don't want to go through the code. It comes up with a nice polynomial that comes through a set of points that you're giving me over this finite field. Lagrange interpolation is covered in a bunch of undergrad courses, but probably not the most common. So it's totally fine if you don't understand what's going on. Take it as a black box, right? Just think of it as curve fitting in a really nice setting. Unfortunately, Lagrange interpolation is m squared, and that gets kind of slow really fast, even though it's not super, super slow. And so maybe we want to do better. Sometimes we can optimize it over specific cases. So if you need to go through specifically 2 points or specifically 4 points, there are nicer optimization versions of this. I won't show you the code for it. Believe that they exist. If you don't, just use this with the appropriate values. Alternatively, there's this thing called the fast Fourier transform, which will also do precisely the same thing. It'll run a little bit faster. It'll be n times log n. So we saved our second factor shrunk by quite a bit. We can also get the inverse of this. And so same problem, different solution, a little bit faster. We're actually going to use both functions, which is why I showed you both as opposed to just saying here's the faster one. And so now let's just make sure we all understand what's going on by looking at a quick example. A fast Fourier transform will give me a specific set of points in the red box up here, right? I need it to go through 3, 1, 4, 1, 5, 9, 2, 6 as my set of y values for the 8 first values after some root of unity, after some starting point x, namely 85, modulo 337. The polynomial that gets returned is this f of t, which has the coefficients in the bottom, and then we can check that we evaluate the polynomial at the same points to get the same y values. And this is all it should be doing. It's totally cool if you don't understand the math of how that works, just that it does work. I'll back up for just a second because I forgot the slide existed. A root of unity is something we're going to need to talk about, unfortunately. We're going to deal with x powers that are successive x values, which are successive powers of some root of unity. A root of unity is just some value such that x to the whatever value is equal to 1 for some modulus, right? So you keep multiplying it by itself a bunch of times, eventually you're going to get a 1 back. And so what we would like is successive roots of unity, so that we have successive execution trace points all being raised to some power and eventually getting a 1 back. And we only want that because that's the only way fast Fourier transform works. This is a requirement of using this optimized subroutine as opposed to a key ingredient of Stark's. But without this optimized subroutine, Stark's could get really big and slow. So we do need to make this complicated math diversion. If you don't still know what a root of unity is, it's totally fine for now. Okay, any questions about how or what polynomial interpolation is? Or modular arithmetic or Stark? Because that's the setup phase. Any questions about mimic? Okay, not hearing any, so I've either entirely lost all of you or I'm doing a great job. Hopefully it's the great job part, but if it's not, please let me know. Okay, so what did we do last time? We spent a bunch of time trying to check low degree polynomials, check out a bunch of points around a low degree polynomial without checking strictly more than the degree of that polynomial. And so we want a low degree polynomial that we can probabilistically be convinced of, say 80% of the points where it's get back are good and on this point. And we need to sort of be a little bit more specific on how or what this low degree polynomial is. In particular, this time we care about the specific low degree polynomial. It's not just how do we solve this problem. Here we want to care about how do we solve this problem in the context of Starks. And so here, what we actually want to be prove to us is that there's some sped up values that are claimed on this low degree polynomial. The root of unity, which is basically where we start counting in our x values of these successive powers of x that eventually go to 1, right? So just some starting point in x. And so we're going to have a bunch of consecutive x values and a set of values. So this looks very much like part 1 in the sense that, we cared about what happens to the valuation of p even the first million points, right? Set of values is like at most 1 to 9. And the roots of unity will be the first million roots of unity or first million points if we just want to abstract away that term. A low degree polynomial, like the degree of the polynomial that we want to be low, and of course the modulus because the finite field we're working on, so we keep things small. Right, so we care about the specific low degree polynomial as opposed to how do we just do low degree tests in general. And how are we going to do this? Well, we talked about a lot of ways to solve this last time. It was sort of this one really big operate square thing, and then we did this recursive thing. And basically, we're going to do exactly that, except, of course, we can optimize it slightly by using recursion. First, the degree is sufficiently low, let's say 4. I'm just going to provide the entire list of values to you. I don't particularly care what happens because to test for a low degree proof, if it's sufficiently low, I'll just give you more than the degree. And so if my degree is 4, I can just give you 6 points, say, and then you're done. Right, and you're pretty happy with that. And otherwise, if it's really large, then we'll do what we did last time. And that was a complicated math that looks something like this, right? And this is the most complicated version of that math, or this recursion of rows going back into recursive cases and so on and so forth. But that's fine because we're defining this recursive definition. So now I'll just take a quick pause to say, Sebi asked last time, how do we know that the values we queried on a specific row or column were of some low degree polynomial? And that's because of what I just said for the base case. In the cases where we queried a specific row or a specific column, we actually queried for more points than the degree of the polynomial we expected to be on. So it definitely would satisfy this equation. Note that the degree of the stuff for the column or row was something like 1,000, but we were trying to get a general result for some polynomial of degree 10 million. So even though we were doing more than the degree for some polynomials, we were doing strictly less than the number of checks for the degree of the polynomial we actually cared about at the end of the day. I don't know if that actually answers Sebi's. Debbie, did you get that? Or do you remember your question?
Yeah, I do.
Is that answer satisfactory?
Yeah.
Okay.
Thanks.
Because I think a lot of other people have that too, and I remember butchering the answer, and so I think I want it to be very fair. Again, if you're still totally lost about what we did last week, take it as a black box. Who cares? Let's move on. We can always dig into details when you start to implement one of these, and of course, the easiest way is to implement one of these. This code that Vitalik runs is available online on the Ethereum GitHub, and you can just try it and try to break it until you understand what's going on. It's another approach to this presentation, but the theory matters more than the concrete implementation because the implementation will vary from application to application. because the hard part, which I haven't really got it yet, is the fact that most programs won't be arithmetizable, which is to say they won't just be cubing or inverting cubes and adding things. They're probably going to be a much, much harder thing. So understanding the theory, at least at the high level, is I think more important than getting this specific start to. Okay, once we have that, well, we need to do something special, right? We need to get our consecutive set of starting points, these roots of unity, as we've been calling them. And so there has to be some way to do this. Turns out there's some way to do this. It's totally fine. And now we're going to use our special trick from last time as well, where we're going to let p of x be some other bivariate polynomial xy, where we'll assume or we'll define this other thing to equal p of x in the case when y is equal to x to the 4. And this is really nice, basically just because the math shows up, right? And so this gives us the base case sort of for not quite free, but much shorter because it's a small constant number of things to check for degrees of polynomials, especially if it's only got 4. That's totally fine. But also because for 4, there's only like different 4 types of x that can actually be your possible inverse. So that's kind of nice. Here, if it's unclear why this is how it is, again, just take it for granted for now. And this, in the base case, we'll just use Lagrange interpretation in the special case of 4, because that's why we have that special case where n is equal to 2 / n is equal to 4. In this case, we're calling the 4 version, and it gets us out of the base case a little bit quicker than FFT would. And that gives us a set of x values that we care about. Almost. It gets us the roots of unity. What we're going to do is we're going to take our step of executions. Say if we have 1,000 sets of execution, we're going to put every one of those executions onto or associated with or map it with or map it onto or some other phrase that is mathematically precise. We're going to associate each one of these execution steps with one of these we're going to identify each one of these execution steps with one of these roots of unity. So we have to find where these roots of unity are, and they do exist because we picked our prime to be very nice. It had this 2 to the 32 subgroup, which is nice, which also means that if our execution takes longer than 2 to the 32, we're probably not going to be able to prove anything about this because the behavior is not as we expect, but 2 to the 32 is enough for now. And if you don't want to bound yourself with such a short thing, just find a bigger prime number and do this all over again. It's fine. So we have our starting point of roots of unity, right? That's good. We do want to commit to these things. We don't want to make sure that we cheat and use different roots of unity later if there are some. So we are going to commit to these, and we're going to build this into one of these squares that we had seen sort of 2 or 3 slides ago. We're going to build this low degree polynomial proof, which is this Frey proof, which is the big thing we talked about last week. It's fine. Just code to do that. And then with that, we're actually able to look at what our actual Stark does. So the make proof function that we're going to have, which I've removed the signature for, first starts with some very trivial asserts. First, let's make sure we have a nice set of steps, which is bounded by 2 to the 32, right? This is what I said, that we can't necessarily prove anything after 2 to the 32 steps. So if your computation, if you want to run Mimic for more than 2 to the 32, maybe you need a new prime. In fact, you almost certainly do. And then, we'll also just make sure that it's a nice power of 2 for convenience. That's fine. And we want to make sure that our number of round constants, that polynomial k that we talked about on slide like 4, has at least, or has fewer than steps count, which is totally fine. Because if it goes over that, you wouldn't use those values anyway, so you could just truncate it to the first steps value. So that's also fine. Really easy so far. And now here's the big step, one of the first big steps. I try to make call-outs to make them really drive home because the math has probably been killing your brains. Log all the intermediate computation value. So what you do is you literally just build a list. Hey, what was your x values after step I? Put it in after step I plus 1, put it at the end of that. And so you have to build this really long list of values, and you have to do this annoying work. And this is why Starks for general and arbitrary computations are probably still an active interest area of research, is because you need to be able to do this in a nice, meaningful way. Mimic was nice because we only cubed or inverted cubes, in particular inverted cubes, I guess, for the prover part. But it was basically just a bunch of arithmetic operations on a single variable. And of course, it's very easy to create a computational trace of what that variable does over time. You just track one variable. For an arbitrary computation, especially one that would require reads or writes, or memory storage, or God forbid web calls or something like this is probably going to be a real pain. We talk about this slightly more at the end about the overhead that this might incur. But this is why Starks, Jared asked me before it started why, if I think Starks will work in general, and I think no, they're still like 10 to 20 years away, because this step is sweeping a lot of general purposeness away, right? It's saying we can do it in this very specific case, we can't do it for an arbitrary program just yet. Even though the computations we actually run may not be restricted, and you might be able, like you should be able to encode other computations like this, just getting this to work in a nice, meaningful way probably means you guys have to agree with your prover and verifier that like, oh, you're going to take the variables in this order, or you're going to use this compiler or something like this, in which case you add overhead and really, really annoying factors. But for now, assume one variable, log all of its values for all the number of steps you run. Simple, right? This is, again, slide 2. This isn't new. Convert that into a polynomial. We have a bunch of points, right? X goes from 1 to 3 to 7 to 9, I don't know, whatever the actual cube's values were, right? And then we do all this code, which I sort of glossed over and said we're going to use as a black box to make a polynomial out of a set of points. Well, we have a set of points, and we have a function for making a polynomial that goes through those set of points. Boom, do that. Using those special values of X that we just determined 2 or 3 slides ago, right, where the roots of unity start as our X values, we're going to associate each one of those with a point or an evaluation of X during some computation of this mimic function, right? So this is just a simple call to the fast Fourier transform, and we're fairly clear with this so far. I mean, it is to me, I guess I don't know if it is to you. The next slide will make it a little bit more graphical, and then I'll stop for questions. So you can think of this nice multiplicative group on the board as certain values, which loop around because it's a finite field, and so they eventually loop down back to where it started. It's like a clock, but with many, many points. This is not our actual prime. Our prime has many more digits than this. I don't know that it's an abstraction. And then basically these X circles are these roots of unity, and we want them to be values that have some specific property that if you raise them to some exponent, they go down to 1 in subject to our modulus. And so they're not necessarily consecutive values, but they do exist somewhere in our group. And we basically find those values. And for each one of these black circles, we associate a value of our computation. So like at step 1, G1 represents like the polynomial P of X at step 1 gets me what the initial value of X was. At step 2, we look at the next consecutive value of this root of unity, or the next consecutive power of this root of unity, so G1 squared. Third step, G1 cubed, et cetera, et cetera. We know that this is fine because there are at least 2 to the 32 consecutive roots of unity, and we've bounded our steps by 2 to the 32. So we won't run out of black circles before we run out of steps of execution. This may have lost some people. Any questions, concerns, comments? Anything I can clarify at all? Okay, we can ignore the orange circles for now. I'm not hearing any of the questions, so I'm going to move on. Now we're still trying to build a Stark. What do? Well, we have to get a little bit more polynomials built. So remember we had these bunch of round constants. Well, I can make that a polynomial as well. There's 64 points. I can use fast Fourier transform or Lagrange interpolation, to build a polynomial that goes to these points. That's what this does because we're dealing with polynomials. So we're doing polynomial representation. Just converting that to a polynomial. Right, and now we're going to use tactics from part 1. And so now we're trying to define, we're trying to say that you ran P of X in some nice way. And so remember we did this by sort of treating and saying we're going to say, well, make this new function c of p of x that can be composed into z times e of x, and we're going to do exactly that same trick because there's sort of no reason not to. We have a series of executions for which the new value is the old value, like the new value minus the old value is equal to 0. That's a polynomial because our new value is an arithmetic operation on our old value, so it's a very nice polynomial. And so what we would really just like to see is that we can have some nice function c of something, and you're basically going to try to show me that you did p correctly, and in this case k, but k is sort of well known, so it's totally fine. And so how do you define c of p of x, where p of x goes to 0 over some values? Well, you can define c of p of x to be precisely this, where you basically take the new value, which is p of g1 times x. You can think of that as your new operation, minus the old value minus the thing you just added to it, right? And that should always equal to 0. And so now you have an inside polynomial that always goes to 0 when you want it, and it looks exactly like it does before. And so now you're trying to show that this always goes to 0 on the range of values you care about, namely the range of values between step 0 and step number of steps that you're asking for, right? So if you assume that you asked someone to prove that you did this for 7,000 steps, then you know you'd care about the first 7,000 steps. And here's the code to do that. Again, not actually that hard, although the interpretations are kind of not obvious, right? Because these names have weird things in their polynomials. Oh, I sort of jumped ahead in my speech. Yeah, so p of x1 times minus p of x cubed minus k of x equals 0. That will be the q of x function that we're trying to show that we know something about, right? Slowing that down a bit more, but abstracting away from the code, right? We want to show that we can do, or that we know d of x for some d of x, right? Because now we argued before that c of p of x should be equal to something that goes to 0 in some particular set of values, which means that it's a multiple of some function z of x, where z of x is the very easy polynomial of x minus I for each of the first steps number of i's, right? This is z of x, x minus 1 is the first step, x minus 2 is the second step, so on and so forth. So z of x is sort of well known, and you need to show that you know d of x, okay? In step 1, we were actually pretty content that this worked, but we swept away under the rug the fact that if I randomly choose values of d of x, you might actually still believe me, even though you shouldn't believe me. The checks don't actually fail. And I never went into the attack in great detail, but that's sort of what I tried to do in part 2, and then part 2 developed all this additional math that we're trying to use. The problem with the part 2 math is that they take a bunch more time than just the part 1 math does on its own. And so we don't want to necessarily do part 2 every single one of these polynomials, because as it stands right now, you need to do it for at least p and at least d, which is 2 things, which is kind of annoying. Maybe we can do better. In fact, for sure we can. And in particular, if you're still lost about what part 2 is doing, basically, if you look at this function, q of x is equal to z of x times d of x, right? You're trying to show that you know d of x. Well, you can always divide q of x by z of x, but the problem is it's not always an actual polynomial. It might not always divide evenly, right? There might be a remainder. And in the cases where there's a remainder, the attacker gets to be malicious and screw with you. And so all of part 2 says is that, oh, you definitely didn't get a remainder. And that was so much work, but it shows that it's not a remainder. Encoding it, not super hard. Once we do all those functions that we've already defined, I think I've just defined the fry code for you already. If I haven't, slide missing, I'll add it. But now we just got to check everything that works, right? And you also want to do the boundary checks because we want to make sure that all these points are on a low degree polynomial, but not just any low degree polynomial, the one that we cared about, right? The one which started at the initial value we gave you and ended at the exit value you gave me, because otherwise you just proved that you did some execution for some amount of time, but I didn't care about any execution. I wanted specific executions, namely the one you said and the one I told you to start with. And so we check this for P and on D because these are the 2 polynomials that matter, right? But unfortunately, these are kind of problematic. As it stands, there's no way to enforce that P and D agree where they should be on the first and last points of data, which is extraordinarily annoying. So we need to do a little bit more work. Not too much work, a little bit of work. We're just going to define the line that starts at one initial value and ends at steps, comma, output value, right? So this one input and last output. And we're going to draw that line. And then I just want to make sure that p of x, which is my actual polynomial that you've given me, minus that is 0, right? And now you could just check that maybe without a polynomial, thinking, why do we need an actual polynomial? Well, because we need to sort of check things along the way as well. But now the problem is prove p of x minus I of x is a multiple of this nice thing that we have. And in some visual terms, we have this. So you give me p of x, which is the purple line on the top left, my top left, it's your top left. The green line is this interpolant that we define as the line between 1 comma input and last comma output. And then the red line is just p minus I. It's fine, it just sort of makes it nice and flat, but not super flat. And then we define some other polynomials that sort of matter to make sure that everything checks out. Particularly this yellow polynomial Z2 checks that. So let's start with the red one. The red one is still the same, p minus I, which is the same polynomial. And then we're going to have this other b value that should have this interpolant matching the execution in a way that relates to some minimal polynomial that goes through it. And so this part I've sort of swept under the rug again. But actually, if you notice the code, it's just sort of defining the nice polynomials that make this calculus work. So in the interest of time, I won't go too much longer than that. Once you're done that, all you have to do is commit to saying P, D, and B, because these are the polynomials you want to prove to me. P and D are obvious. B is this one, this auxiliary polynomial that makes this argument work, which is just some combination of these. You could do 3 separate proofs some last time to do this, but that's a lot of effort. Those proofs take effort. So what you do is you just make a random arbitrary linear combination. You guys remember linear algebra for these polynomials, and you commit to a single proof of that, and boom, you're done. That's basically Stark. Yeah, I'm gonna skip ahead. This is what the actual thing looks like. You get some output that is 4 arguments. It's less than 500 kilobytes long. You've convinced me that you've run some code for some time. Any questions? Before I just go back and recap the slide I skipped. What can I clarify? There was almost certainly non-trivialities there, and I would like you to understand how these things work.
Would be interesting to see what the relationship with VDFs are, or what such a degree polynomial would be useful for. Or such a, yeah, why would you want to prove that you know a polynomial? I don't know.
So,
I think you mentioned it before,
okay.
but I forgot.
Yeah, applications are actually fairly straightforward, especially in this case, the mimic VDF in some sense computes a hash if you think about it. If you don't know what the number will come out to at the end of time, unless you actually try it all. So if you go to the step, right, what you do is you basically say the VDF is proving. So you just take some input, you invert it a whole bunch of times, and it takes a long time to do that. And so you can commit to running this code and the input and then not know what the random value is. So for example, I could use this as a beacon, as a randomness beacon. So I commit to running mimic in this reverse fashion, which is the inversion fashion, with some input. And then if that number is even, I will award you $10,000. And in fact, assuming I haven't done this off chain somewhere, I can't check what the value will be ahead of time. So especially if I ask you to give me a function or someone else to give me a function. But if you give me that function, I can run it, or if you give me the output, I can verify it to you very quickly whether or not I actually have to pay you, because the opposite direction is 100 times quicker. And so even these simple polynomial arithmetic operations do have a little bit of application. In the VDF case, they're particularly helpful in the DEX case, it's maybe less clear. But anything that can be arithmetized is doable, and this is one that's reasonably doable because we just did it in Python. Whether or not there was issues in the code or small bugs or whatever is another story. But this is sort of old math, right? It's solved. Here's the solution. So yeah, there are interesting applications.
All right, thanks.
Any other questions? Okay, so we skipped a slide or two. We commit to these polynomials and make a linear combination. That's this slide does. If you do your linear combination correctly, it's extraordinarily unlikely that anyone will be able to forge this in some way, because to get terms to cancel, things have to go exceedingly right, which probably won't happen. Proof for that. And then you do these random spot checks, right? This is part one again. You want to take some random small number of checks, and you get the start. The verifier runs a code that looks like this. I can fit it on the slide. It's pretty good. Checks the boundary conditions, checks the proof. Obviously, there's a little bit going on here in terms of Merkle root reading and verifying branches, but it's not super hard. That concludes the highest level of Starks I can give without, doing away with any math, and the lowest level I want to go into without providing actual theorems and proofs and QED symbols, at least the ones that I could find, and I didn't want to spend hours and days coming up with my own material because I don't think that's interesting. What we noticed here is that our mimic overhead, or what Vitalik noticed, I guess, it ends up costing us about 400 times, like a factor of 400 in terms of processing speed, which is not ideal, but it's pretty good. I mean, it could be worse. This function is not the slowest. He posits for general code, which may not be so easy to arithmetize, which is to say use only arithmetic operations for. It's going to be closer to 50,000 times overhead, which causes this approach to be very limited in scope at this current time. We saw several cube math problems that we needed to overcome: low degree testing, error amplification, and polynomial interpolation to a certain degree, although that's an old problem. And we also saw that the size of these proofs are kind of varied, although not explicitly. The proofs here, for this example, range between 250K and 500K. For larger pieces of code or information or longer execution steps, this grows. This is also where it starts to get costly to do this on chain, and which is why this approach has only really been attempted for roll-up solutions, which are solutions that batch a bunch of things and then do it one proof for a bunch of batched operations and then submit the proof. Because this enables you to spread the cost of putting that single large proof on chain amongst thousands or hundreds at least of users or transactions who are willing to pay a part of this fee. The math, whether or not you believe me or I went through it too fast, I don't think is that hard. The hardest we had to deal with was a little bit of probability, a lot of polynomials, and some interpolation, most of which would almost certainly be covered in like a third-year pure math course at sort of the best case scenario if you cared about this, and probably only a sixth-year course in the worst case, which I think is pretty simple. There's a lot of areas of math where you can dig for 20 years before you need to understand what's going on. And here, the fact that we've reduced it all to fairly simple polynomials, which again, maybe you don't understand exactly what one specific polynomial did at this point, it's not moon math. It's here's polynomials, find some roots. It's relying on a bunch of things that are really, really well studied. I think that this is a very interesting part of how privacy and will be achieved on a blockchain, but I do think it's a long way out. And I do think that we, specifically as a company, should not shy away from taking projects that rely on this, because with a little bit more time and effort, we could actually be doing these on our own if we needed to. We just don't have a need for it. The math is not. I'm trying to convince you the math is not super hard. I don't think polynomials are hard. Right? If we're only really caring about group theory and calculus, it's something that's that bad. But that's what I'll just say at the end. Any questions about Starks or anything, now is the time. There won't be a part 4. There is a lot more reading material. I will append to the links the link to the presentation. It's very well studied. But yeah, questions. Now is a good time for general questions. I'll stop there. Okay, well, I'm not hearing any. I'll be around for the rest of the day. Please send me messages, especially if you didn't get an answer to a question that you had before, or if you're still completely lost. Those are the 2 particular cases I care about. If you've got some part of this, then hopefully now you can at least have a high-level understanding of the Starks go.
I would have some general questions, actually. Sorry.
All right, this is the time, yeah.
So you implemented this on your machine, right?
I didn't. Vitalik did.
Oh, okay.
I mean,
I thought you tried it out.
It runs, it compiles, there's nothing.
Okay.
Yeah.
Would you see this kind of thing being used somewhere inside of QuantStat? Do you think like it would be useful for one of the products that we have, or any potential product that we could develop?
So at this point, no. Mostly because what we do is a lot of security related stuff, and I'm not sure you could arithmetize a SAT solver with any great ease, right? And so this works nicely because you're only cubing or taking the inverses of cubes of values. As soon as you A, have more than one value, it's troublesome, and B, as soon as those things need to operate in some ways that aren't purely arithmetic, it gets really complicated. So, right, even just like putting up an if statement into one of these blocks would suddenly make this incredibly more annoying. And so, unfortunately, the products we seem to be shipping right now just involve better, more interesting code, which therefore probably can't be arithmetized in any nice way. So until this is overcome, I don't yet see it. I would like us to keep thinking about it, but I don't see the immediate application.
All right, thanks.
Okay, thanks guys.
Thanks, Jan.
Thanks, Jan.
Thanks, Jan.
Thanks.
Bye.